All right, so we're back. So just so everybody's clear of what's going on, so you all are going to have a homework assigned on Wednesday. So today, probably today and going into next time, we'll finish bolts. And if we haven't finished bolts by Wednesday, we'll be darn close to doing it, okay? We have two big topics that we need to discuss with bolts. One of them is slip critical bolts, which we'll talk about today, and the other is combined loading. What happens if you have a bolt that's seeing not only shear but tension as well? You got to be able to handle both. So that's what we're going to talk about for the next couple days. So on homework 4, which is going to be your bolted connection homework, there's probably going to be maybe 3 problems, maybe 4 problems, something like that on bolted connections. So I mean, I know it's been a while since we talked about this, but it is coming. All right, sound good? All right, so let's get into slip critical connections because that's sort of where we left off. So let me just sort of spend a little bit of time. Sign-in sheet, thank you. Going over all this. I even was thinking about it a little bit ago, and I completely forgot about it. Thank you. Those sign-in sheets passing around. Okay, I spent all this time talking about the exam, and it's been a while since we talked about bolts, and I thought it'd be a good idea to just sort of recap what was going on with bolts. I'm going to start here. Okay, so if you recall, up until now, we really only discussed 2 limit states associated with bolted connections. We've either discussed bolt shear or bolt bearing. Okay, now they're pretty straightforward. Bolt shear, we're talking about the shear or the bolt shearing in half or snapping in half, and for the plate, we're talking about the plate failing, either the plate or the hole stretching out a little bit, bolt hole ovalization, or the bolt or the plate literally being tore out. So we have bolt tear out and bolt hole ovalization. Now for design, so far, it's been pretty straightforward. We determine our load, we determine the shear capacity of one bolt, then we divide to obtain the number of bolts. Pretty simple, okay? We lay out the connection according to minimum spacing, maximum spacing, and edge distance requirements. That does not guarantee that we've met bolt bearing. We check bolt bearing, and then that's essentially it. I think our last example we did was this, and we had talked about even stuff that gets pretty basic, things like prime numbers. Remember, trying to make sure that we're not picking 13 bolts and have some massively long connection. I mean, we got 15 bolts, I think, for this connection, so we just did 3 by 5, keep it in a nice tight grid, and then check our bolt bearing later. And then we talked about some other detail-associated issues related to splices. Any questions? I know it's been a while since we talked about this, but it is coming up. So, everybody good? Okay. So let's talk about a slip critical connection. Now, let me be clear on this part right here. So to design a bearing type connection, you determine the load, get the shear capacity of a bolt, divide to obtain the number of bolts. Okay? Designing a slip critical connection is no different. Okay? The only difference is, from a procedure standpoint, is instead of looking at the shear capacity of a bolt, we're going to be looking at the shear capacity and the slip capacity of a bolt. We just take the minimum one. So the design procedure is very, very similar. Okay. Now, slip critical connections are the other, I guess I would say, primary type of connection that we use in steel structures. So bearing type connections, if you recall, a bearing type connection literally requires the bolt to come into bearing with the plate. So you have a hole, you have a bolt, and when I load and shear, the bolt literally loads the plate, like physically comes into contact with the plate. It bears on the plate, hence bearing type connection. Okay. Now a slip critical connection is a little different. Slip critical connections rely on the friction that develops between what we call faying surfaces to safely resist load. Now faying surfaces, I mean the surface where 2 plates come into contact. So let's see if everybody can kind of grasp what's going on. We've got plate A, plate B. I put them together. Okay. I have a bolt going in between them. Put the nut on this end, and I start tightening them. Okay. Now imagine I've got this massively powerful wrench, and I'm really wrenching on that bolt to get that bolt super, super, super tight. What's happening to the plates? If I have a bolt going in between them and it's really tight, what's happening to the plates? Squeeze together, right? So much so that I could probably develop a force in between them, right? Remember that whole concept in statics, or not statics, but physics? Actually, it was actually both. Remember, you have the static force that develops between two planes is a common or a product of the normal force between those two planes and a coefficient of static friction. Remember that? Well, essentially, that's slip critical connections in a nutshell. Now, critical connections are really meant for, I would say, two primary instances. Number one is fatigue. So the easiest way to describe fatigue is, imagine you've got let's say you got a lawnmower, one of those push mowers, on your lawn. And there's nuts and bolts all over that place, right, in one of those. Well, imagine what happens if you have a bolt on there that's very, very loose, or somewhat loose, let's just say. And I start the lawnmower up, and I start mowing the lawn. What do you think is going to happen to that bolt over time? Vibrate off, right? So the lawnmower is going to, and over time, got another sound effect in there, right? I got plenty of them. So what's going to happen is, over time, that bolt is just going to get loose. And it's going to screw off. Now, what we're talking about are connections that are holding up large-scale structures. We can't have that happen, right? So in a structure where we have fatigue considerations, we're going to use slip-critical bolts. Quick question. What's one type of structure do you think that fatigue considerations are going to be an issue? A bridge. Bridge has cyclic loading. It sees loads over and over and over again. Now, it's not like the lawnmower where all the vibrations are happening over a very short period of time. Bridges are seeing cyclic loads. It's just drawn out over years and years and years. It's not vibrating as fast. It's not really, we're not talking about vibration, but it is seeing cyclical loading over an extended period of time. So we have to ensure that those connections are super, super tight just to facilitate its performance throughout its design life. That's one instance. Another is earthquakes. Now, earthquakes, I hesitate to say that you design all earthquake-related connections as slip critical. More often than not, you're detailing them as such. In other words, you're drafting out the connections and constructing it so that it's slip critical, but you actually don't have to pick that many bolts. Usually, the difference between a connection that is designed as a bearing connection and a connection that is designed as a slip critical connection is that slip critical connections, by and large, you need twice as many bolts, because you're not able to develop as much force between those plates than you are if you were just trying to snap that bolt in half. In other words, if I'm in the lab and I got two plates sandwiched together and I got a slip critical bolt and I yank on it, I'm probably going to fail that frictional force before I fail the bolt. Does that make sense? I can only get so much friction, so it's a little weaker in that regard. All right, sound good? Yes, sir.
So what happens when the frictional force fails?
When the frictional force fails, so here's what happens in the lab. Okay, so you've got plate A and plate B, put them together, stick a bolt through them, tighten them up, right? And you've got them really tight. Okay, and you start loading it. Okay. Now, what happens first is you're going to fail that frictional force before the bolt comes into contact with the plate. In other words, here's the hole, and the bolt is just sort of sitting there. It's not coming into contact, right? It's sitting there, and the friction's holding it there. Once you fail that frictional force, it goes like that. And if you're in the lab, you'll hear a boom, like a big boom, because it suddenly comes into contact. But then, as soon as it comes into contact, it stops becoming a slip critical connection and it starts becoming a bearing connection. I'm not saying the connection is going to fail. What I'm saying is that it stops doing what we're intending it to do, because then there's no more friction. Does that make sense? Is everybody else okay with that? Yes, sir.
How tall would a building have to be before it's fixed enough sway to apply a slip critical connection? Like you design a skyscraper, it's going to sway even if it's 1,000 feet tall.
True, true. But I see where you're getting at. What I'm saying is that in an earthquake, the forces that we're seeing due to an earthquake are far larger than what we're seeing in wind. Okay? The concern you're raising is about, well, if you've got a really, really tall building, you're going to get massive, massive wind forces. What I'm saying is that in that scenario, you're just going to use more bolts. That doesn't necessarily mean you're going to use slip critical bolts. Okay? Slip critical bolts, that's a different story. Okay? Does that make sense? Is that a fair way of answering that? Again, I'm not saying you don't have a lot of force. I'm just saying you might not always use slip critical connections to resist that force. Fair answer? Fair good? Everybody good? All right. So again, the theory is pretty simple. Frictional force, or a coefficient of static friction times normal force. So it stands to reason that the amount of force that you develop between two plates is a function of the coefficient of friction, so the surface, so steel on steel, what's that coefficient of friction, and the normal force. In other words, it might have something to do with how tight the bolt is. You know, what does that mean? I mean, in other words, if you're using a wrench versus if you're using a wrench, you might have bolts that are at different levels of tightness. See what I mean? So to achieve this normal force, we have really a two-step process. So we get the bolts snug tight. Now I say snug tight, and what is snug tight? Here's what snug tight is. Snug tight is either a few hits of the impact wrench or basically the full effort of a given iron worker to get that connection snugged in. There's no real super codified definition on what snug tight is. The reason why is because that doesn't really matter. Once you get the bolt snug tight, you've got to use one of the prescribed methods to achieve the required torque. Now, what are those prescribed methods? Okay, there's a number of them. Okay, I'm going to show you a video. I think I have a copy of it on the V drive. But one of them is called the turn of the nut method. This is probably one of the most common ones because it doesn't really require any super specialized equipment. Some of the others, they require the equipment that you use is a little more specialized. But you can do things like using a calibrated wrench. In other words, a special wrench that is calibrated to produce the required amount of torque. You can use special type of bolts, twist-off tension control bolts. That's one of them. You can also use a direct tension indicator. A direct tension indicator is basically a fancy washer. Has these little nubs on it. When the nubs mash to a certain level, you know you've hit your required tension. Everybody with me so far? All right, let me show you this turn of the nut methodology. So I think the easiest way is, I have a slide on it, but I think the easiest way is, let me see if I've got this video. I do not. So I think it's on YouTube. I will try and find it, and if I can't find it, we'll just move on. This is this. Okay. We're going to have to change that to... Okay, that didn't work. What? No, I know, but I should hear a little... See? There we go. All right. So this fabricator is working to install these particular bolts using a slip critical methodology. The first thing that he's doing is he's getting the bolts snug tight. So it's just a few hits of the impact wrench. Now, if you notice, what he's doing is he's marking the bolt and he's marking the nut. So the idea is once he does that prescribed turn, he'll be able to visually see, okay, this is how much that needs to turn. And that wrench he's using is really just it's just a really powerful wrench. You can see it's just sort of, there you go. That's basically it. See, if you notice, he's got this sort of red guide on there that's helping him line up, how much that needs to turn. And it's really just a lookup. You go to the RCS spec and say, all right, here's my bolt diameter, group A or group B. I need to turn it an extra third of a turn or half of a turn. That's it. That's basically all there is to it.
Why is the
Yeah,
the bolt.
it's grabbing. But it's grabbing and turning.
Counter to the direction that the sun is.
Oh,
Yeah.
Right.
Yeah. All right, so for instance, for this example, oh, I want to go back to this. So for instance, for this example, that particular bolt needed to be turned a third of a turn past, snug tight. So if you notice, you can see here was the mark that was placed on the bolt, and there was one nut right here. And then that wrench basically just yanked on it until it got that third of a turn, and then that's prescribed tension. It's one of the easiest methods that's used. If you go to a fabricator and you see a bridge splice, once it's done, if you look in the field, like once it's done, you'll see these little paint marks all over the place. That's what they were for. They were there to get those bolts to their prescribed torque. Sound good? This is one way, and I would argue this is the simplest way because they're 1/16 of an inch. That, no. That's
the slide says use oversized or slotted holes.
That's a good question. So we're talking about, when I say oversized or slotted holes, I'm talking about things like on a bridge where you have an expansion bearing. So maybe to allow a little bit of potential movement, you might have a slotted hole. More often than not, in most structures, we try not to use them. So, I mean, they have their uses here and there, but
'Cause I mean, maybe it's just, I'm thinking it completely the wrong way, but wouldn't it just be a factor of over tightening the bolt where friction factor comes in? But maybe I'm not even
I-
thinking of the right thing, who knows? But you just said if you over tight, or the tighter it gets, the more friction there is, and then once
Yeah.
the friction factor fails, then that's when the bolt in contact with the,
that is correct.
and there's a 16th of, actually there would be another 16th of an inch.
Well-
Just ignore the question.
No, I don't understand what the question
I'm
is.
still trying to define in my mind, like, if the bolt hole's the same size and a slip critical connection, then there shouldn't be any space in between to where that bolt.
No. Remember, we don't put a half-inch diameter bolt in a half-inch diameter hole. You couldn't do that anyways. That's why we drill the hole a little bit larger. Okay? Does that make sense?
Yeah, I know.
Okay. Yes, sir. Okay. This is what I'm all right, you have plate A and plate B coming into contact with one another. So they've got a lot of force in between them. Now, you grab this plate and I grab this plate and we do that. Okay? Friction keeps it together, but only for a certain point, and then it slips. Does that make sense?
And that's when the bolt folds up.
What?
That's when the bolt kicks up.
Yes.
That's what.
Yes. I mean, like, literally, that's what I'm talking about. That's what slips. Does that make sense? Everybody else okay with that? Yeah. Wait, the hole in the plate. The hole is in the plate. They are. I'm not talking like a bolt hole that's like 4 inches larger than the bolt. I'm talking like a 1/16 of an inch.
That's gonna be a 16th of an inch on each side, so really on each side.
Actually, well, yeah, 1/3. Yeah, we're not. I mean, it's going to be. Well, it's loud. But do you want it to be dramatic? All right. Okay. Now, a couple other methodologies. One of them is the use of a calibrated wrench, and you can use a wrench that's calibrated to use a very specific torque. The way that you calibrate them is you basically stick a bolt inside of this thing right here. This thing is called a Skidmore Wilhelm, and if you want a definition for what it is, it's basically a super duper hyper accurate bathroom scale for bolts. So you put a bolt in, you tighten it, and then it measures the force. So you use a wrench, and then you say, okay, I'm going to be installing 3/4 inch diameter bolts all day. So you use it on that machine, and that machine is basically reading like a bathroom scale, and it will tell you when to stop based on a prescribed torque to reach that given tension. That's basically it. It's pretty straightforward. There are some other niftier systems out there. This is one that's probably a little more expensive, but I would argue is much easier to install. So this is a twist-off control bolt. It involves the use of a special wrench and a special bolt. So if you notice, the bolt kind of has this sort of splined end. See how you've got the threads, but see how there's this kind of end right here with this little nub on it? Does everybody kind of see that? So what happens is you use this specialized wrench, and the wrench grabs not only the nut, but it grabs this little splined end, and it starts tightening, okay? Once it reaches that prescribed tension, the splined end actually just sort of breaks off. So it's really easy for an inspector to come out and say, all right, here's this connection. This one still needs to be tightened. This one still needs to be tightened. These two are good because it broke off. It's very fast to install. It's also a little expensive. So, which is more important, time or money? Well, it's a trade-off. It just depends on what you're working on. Sound good?
Maybe some inconsistencies on the strength of that bolt.
You're exactly right. We're actually going to talk about that here in a little bit. But the inconsistencies are they actually work more in our favor than they do against us. Okay? More often than not, what you find in the field is the amount of torque that we rely on versus the amount of torque we actually get. We actually get a whole lot more. So much more that the amount of torque that we rely on, we actually bump it up 13%, because statistically, that's how, people tend to wrench on bolts like crazy. I guess it's just sort of common practice. Sound good? All right. The last one I think is worth mentioning is a direct tension indicator. A direct tension indicator is really just a very special washer. The idea is that you have these gauges that will measure the distance between this gap right here. So before and after tightening, those little nubs on that washer will mash down, and once they've mashed down a particular distance, you've hit your specified torque. There are all sorts of specialized ones. Like there's ones that have, there's these washers, and they kind of have these little grooves in them, and they have this sort of like this orange goop that's inside it. And then once you start tightening it, those nubs mash down, and the orange goop starts to squirt out. So if you're tightening, as soon as you see the orange goop squirting out, you're like, all right, I'm good. So there's a whole industry with trying to achieve this. So yeah. All right. Sound good? Okay. All right. So let me explain how we determine nominal capacity. Now, one thing that's kind of strange is that our phi factor is 1. And that's probably an odd one for us. This is one of the few instances that we will actually use a phi factor of 1. The reason why we use a phi factor of 1 is because if a member or a connection fails in slip, it sucks, but it's no big deal because the bolt can still take over, okay? So it's not as much of a drastic concern as if we're talking about bolt shear failure. If we talk about bolt shear failure, the bolt is literally snapping in half. This is just a failure of friction, so it's not as big of a deal. All right? Now, this equation's got a lot more going on, but it really is just coefficient of friction times normal force times a few adjustment factors. So number 1, mu, our mean slip coefficient. That's the coefficient of static friction, okay? T sub B, this minimum fastener tension, that's the normal force. That's how much tension is inside the bolt. Think about what's happening. If I take plate A, plate B, stick a bolt through them, and start tightening the bolt, the plates are mashing together. But what do you think's happening to the bolt? The bolt's wanting to stretch out. It's wanting to get longer. Does that make sense? So the way that we go about this is we try and achieve a given fastener tension inside the bolt. Now, D sub U, this is an adjustment factor. This is 1.13. I'll talk about that here in a second. We have H sub F, which is a filler plate factor, and we also have the number of slip planes. I'll talk about each of these. All right. Everybody good so far? All right. So number one, mu. So mu is our coefficient of static friction. This is essentially going to be a function of the surfaces of the steel. In other words, we're getting friction by having steel come into contact with steel. Okay. So more often than not, we're going to be dealing with a Class A surface, which is just regular old steel coming into contact with regular old steel. So our mu, we take our coefficient of static friction to be 0.3. But if we need more frictional force, we could actually use something like a sandblaster and actually blast clean the two surfaces of steel and get a little bit of benefit. If we do that, we get a coefficient of static friction of 0.5. So a higher coefficient of static friction means a stronger bolt in slip critical capacity. But more often than not, we're just going to go with 0.3. And unless we state otherwise, 0.3 is what we go off of. Sound good? Yes, sir. Well, yeah. I mean, let me say this. So properly installed, I mean, you're taking a plate and sandwiching them together. So first off, when you're bolting it together, the steel's brand new, so it shouldn't be fairly rusty. Okay? And if you're developing thousands and thousands of pounds between these two plates, you shouldn't get much water in there anyways. You see what I mean? So I would say no, it doesn't. Sound good? All right. Okay, D sub U. Now, D sub U is 1.13, and let me explain what's going on. This is what I was mentioning earlier. The amount of torque that you get in the field is actually a lot higher than what we actually specify. So much so that you can actually collect the data and see. I mean, by and large, the lower bound value that we can rely on is 1.13. In other words, on a lower bound average, bolts are seeing about 13% more tension than they really need to. So we count on that. Now, if you're the engineer of record on a job and you go through it or you work at a fabricator and you know that your crew is going to be installing bolts that are 20% larger, you could use 1.2 if you wanted. I don't think that's very common. I think that's a pretty rare occurrence. More often than not, everybody's just going to go with the 1.13. So it's the ratio of the pretension specified versus the pretension we actually see in the field. Sound good? All right. T sub B, now that is the minimum bolt pretension. It's in a table in the spec, but we're ultimately not going to need to refer to it. By and large, the ratio or the relationship's pretty simple. The bigger the bolt, the more tension, or the more tension we need to develop a slip critical connection. And it's roughly about 70% of the tensile strength of the bolt. It's not always, but by and large, that's about what it is. Now, H sub F, that is a filler plate factor. For most cases, we're going to take that to be 1. But the idea behind a filler plate is, okay, so I have member A and I'm splicing it to member B. If they've got different depths, I've got to have a filler plate in there to make up the difference. But if I use a whole bunch of filler plates, well, it stands to reason if I'm trying to sandwich together 5 or 6 different plates, I may not be able to get as much friction than if I was only trying to sandwich together 2 plates. So a whole bunch of plates, we end up using a different filler plate factor. But we aren't going to deal with that. And in most cases, you try and avoid that in fabrication anyways. So we're going to take that to be 1. Last one is N sub S, but N sub S is just the number of shear planes. Just like it's the number of shear planes and the number of slip planes are the same thing, you know. So more slip planes equals more friction. So one of the things to point out is go to your table 7-1. Go to the bolt table. All right. Hopefully you've got that tabbed. So if you go to table 7-1, table 7-1 will tell you what the available shear strength of bolts are. Okay? Now watch this. Is everybody with me on here? Table 7-1? Now turn the page. 7-3. They're right there. That's insane, isn't it? So if you look at table 7-3, there's one on the left side of the page and one on the right side of the page. What's the difference between the one on the left and the one on the right? Group A and Group B bolts. Okay, so it's right there. What faying surface is both tables assuming? Class A. So they're both assuming Class A faying surfaces. So it's pretty straightforward. You got a single slip or double slip, single shear, double shear, standard size hole, 3/4 inch diameter bolt. You can look up your slip capacity. It's that simple. Okay? Pretty straightforward stuff, right? Not too complicated. So when we come back, we're gonna design this particular connection as if it is a slip critical connection. It won't be much different than if it was a bearing type connection. And then the last thing we'll look at is combined loading. Sound good? All right, that's all I got. For those of you not in concrete, I'll see you next time. Otherwise, I'll see you in a few minutes.